torus, okay? A donut, if you will. Maybe you won't, who knows. So, what is Gaussian curvature? Well, it's a kind of way of measuring curvature. Curved surfaces have non-zero curvature. Flat surfaces have zero curvature. Saddle shapes have negative curvature. Dome shapes have positive curvature. Okay, pretty simple, right? So actually calculating Gaussian curvature takes a lot more steps than that, though. This is just intuition. And the special thing about Gaussian curvature is that it's preserved over local isometries, which allows us to say a lot. Like, for example, you can turn a donut into a coffee cup without ripping up the paper that makes it. Well, in reality, you can turn anything into anything if it's filled, but we're assuming a kind of hollow donut. But I don't know if any hollow donuts. Those will probably be really unsatisfying to eat. Okay, I don't know what I'm doing here. So, wait, that might be quoted out of context. Don't quote that out of context. So, let's start by figuring out how to parametrize the torus. Now, from memory, and definitely not from notes that I have written over here, I can say that a torus's parametrization as a surface looks something like this. That was certainly one way to end things off. So, this is how you parametrize a torus, making sure v is from 0 to pi over 2, and u is from pi over 2 to pi. So, we have this over here. Now, how do we get from here to Gaussian curvature? Well, first we have to start by finding the shape operator. But that can only come from finding the unit normal vector field. So let's try and find a unit normal vector field first. So the unit normal vector field is just what? Well, a normal is supposed to be perpendicular, pointing out from the surface and thus from its tangent plane at every point. So that means that if you have the two tangent vectors to the surface in each direction, then their cross product is simply going to be the normal. And of course, you can make these unit vectors, their cross product will be the unit normal. So what are the partial derivatives with respect to, that's not a good phi, with respect to u and v of this? Well, partial u is just going to, where did that come from? It's just going to be, well, a cosine v goes to 0, r cosine u cosine v becomes minus r sine u cosine v. Mostly the same thing happens here. And this gets transformed into r cosine u. Meanwhile, with respect to v, it becomes, well, the last component is just 0 since it's only a function of u and not v. And the other two become, this is minus a sine v, this is a cosine v. Okay, pretty nice. Now, this one has magnitude a, so it'd be very hard to tell. And so, to make it a unit vector, I just divide by the magnitude a to get minus sine v cosine v 0. And you can verify the magnitude of this is 1. And so, meanwhile, the magnitude of the partial derivative with respect to u looks a little bit more complicated, but in reality, it's r times this. And the astute among you will notice that if you square this and you square that, this reduces to sine squared v, or sine squared u, and then adding on the square of this reduces everything to just 1, which means the magnitude is just r. Hence, the unit vector is just going to be everything but divided by r. So minus sine u cosine v minus sine u sine v cosine u. Now we use, I don't know what it's called, Saucer's rule to find the cross product, just a mnemonic involving the determinant of this matrix. It's not a matrix because it contains vectors and treats them like scalar entries. But anyway, you get minus sine u cosine v minus sine u sine v cosine u, and then minus sine v cosine v 0, and you're going to get, well, 0 in this direction minus cosine u cosine v in the other direction, cosine u sine v. Wait a second. This goes. Oh yeah, I'm not stupid. This is minus cosine u sine v, and if you go the other direction, it gives you 0. Okay. Now this gives you minus sine u cosine squared v, and if you go the other direction, it gives you minus sine u sine squared v. So we can reduce this messy looking thing to just minus sine u. And you can verify for yourself that the magnitude of this is indeed 1, because the squares of these sum up to cosine squared u, and this is sine squared u. So you add those two together, you get that the magnitude of this vector is 1. Okay, so this is our unit normal field, perpendicular to our surface, or our torus in this case, at every single point, uv. So now we have to use this to find the shape operator. And the eigenvalues of the shape operator will tell us exactly where, the eigenvalues will tell us the principal curvatures, which will give us the final Gaussian curvature. So what's the shape operator? Well, this is just going to be equal to the inverse of the second fundamental form multiplied by the first fundamental form. Now, recall that the first fundamental form can be written as EFFG, and yes, all of those are scalars. The second fundamental form can be written the same way. Oh, no, it's the first one that's inversed multiplied by the second one. Okay, so what do we get from this? Well, the inverse of a 2 by 2 matrix is easy to remember from your head. This is just 1 over the determinant, which in this case is EG minus F squared, multiplied by, you swap these two, and you negate the ones on the diagonal, and you multiply that by EFFG. Okay, so what do you get? Well, multiplying these two gives GFEF EG minus FF, G minus FFG, GF minus FG, minus FEEF, EF minus FE, and this way is going to be EG minus FF again. Okay, Great. So what are E, F, G, and little e, little f, and little g? Well, E is phi u dot phi u. I probably shouldn't have erased them. F is phi u dot phi v. G is phi v dot phi v. Then little e, and this is where our unit normal field comes into play, is equal to minus unit normal, the partial derivative of the unit normal field with respect to u, phi u, f minus nu phi v, which happens to be equal to the same thing the other way around, and g, which is minus nv dot phi v. Okay, good. So now, well, let's calculate each of these. So, first of all, we have to rewrite phi u and phi v again. So phi u is what? Minus r sine u cos v minus r sine u sine v r cos u. And this way, it's minus a sine v, a cos v, 0. Okay, so phi u dot phi u is just the magnitude of this vector squared, which happens to be what? Well, r squared. We already discussed this. G, on the other hand, is just going to be the magnitude of phi v squared, which is a squared. But what is f? Well, f is, this third term goes to 0, but minus r sine u cosine v, a sine v, gives you ar sine u cosine v sine v. And then a second term, which is minus ar sine u sine v cosine v, which means that this all goes to 0. The two terms cancel out. Okay, so that means we can erase this, we can erase this, and we can erase this, and we can erase this, and we can erase this. Our work has significantly lessened. Now, what's E? Well, we have to actually take the derivative of this for that. With respect to u, that gives sine u cos v, sine u sine v, minus cos u. And with respect to v, that gives expectedly cos u sine v, minus cos u cos v, 0. Okay, so now E is going to be minus nu dot phi u. So nu is over here, phi u is up there. Certainly can't, and nothing bad can happen. This is just going to be minus multiplied by minus r sine u cosine v. And then the same thing happens here, so it's just minus r sine squared u cosine squared v. Did I just say it? Yeah, I'll just say it. If you look closely enough, you'll notice that this is just phi u multiplied by negative 1 over r. Signs work out, everything works out over here. So this is just minus 1 over r multiplied by e. This is just minus e over r, also known as minus, wait a second. Oh, crud. It's minus 1 over r times e. Since, remember, this is minus this dot this, which happens to end up being minus 1 over r this dot this. These cancel out. This ends up being 1 over r this dot this, which becomes e over r. Okay, so this is eg over r, and I don't think E comes into use anywhere else. Great. So, this is E over R, also known as R. F is just equal to what? Well, minus, let's see what I'll go with. Doesn't really matter. Go with 5e, because that's really simple, dot nu, even though the other way is also pretty simple. Okay, so 5e is minus a sine v, a cosine v 0. Multiplying that by this, well, dotting that with this gives minus a sine v, sine u cosine v. Okay, then a cosine v dot sine u sine v. Hey, wait a second, this is 0 again. Little f meets the same fate as its older brother. Okay, and finally, what's g? Well, unlike the first one, wait a second, minus a sine v, a cosine v 0, cosine u sine v. Yeah, this one, if you look closely, is also a multiple of sine v minus cosine v 0. This time, it's just minus 1 over a multiplied by cosine u 5e. Look closely. You'll notice that everything matches up. If you erase these and replace them with a's, it just looks like the negative version of this. So this is just minus cosine u over a of 5e dot 5e, which is g, which also doubles and happens to be a cosine u. But, I mean, yeah, okay. So, we can finally put all of this to rest. Hope I haven't accidentally forgot about something that brings these back. These two go to 0 as well, since little f met the same fate as its older brother, which means you just have this now. Also equal to 1 over r, 0, 0, g over g. And it turns out g over g is just cosine u over a. Which means that the two principal curvatures are, wait a second. Something feels off here. Yeah, I'm missing a term. Should be cosine u over ar squared. So what went wrong? Let's see. Okay, let's go back to the primitive form of these, which was this was eg and this was eg. Okay, good. So this gives what? This is e over e, and this is g over g. So the eigenvalues of this are very clearly either e over e or g over g. Okay, so what if that? Well, it turns out e over e is 1 over r, and g over g is cosine u over a, which means that the answer should be just the product of the two principal curvatures, cosine u over ar. So that's it. Thank you everybody for watching, and we'll see you in the next one.